Okay, welcome to our unit on waves. So this is our first unit where we're not really looking at what we would call mechanics, I guess, anymore. I like to think of waves as kind of more separate than the things like force and energy and momentum and kinematics and all of that stuff. So we're going to take a kind of a step in a very different direction and look at waves. And you did some of this last year, but this unit in particular, there is a lot more that you are going to do this year that you didn't get to last year. So in either case, it's good that we're doing this right after simple harmonic motion because some of the basic stuff does come from that unit. So we'll start off with just the simple stuff. The definition of a wave is a type of oscillation, and you should be familiar with that word oscillation by now because we just got done talking about simple harmonic motion and oscillations, in which energy is transferred from one point to another. Okay, that's all a wave really is. It transfers energy from one point to another. And there's a couple different types of waves that we're going to look at. And specifically, we're going to spend most of our time looking at mechanical waves, but we'll define electromagnetic as well. So in a mechanical wave, what you have is all waves transfer energy. They don't necessarily have to transfer matter. For a mechanical wave, what I would say is matter gets moved, but is not necessarily transferred from one point to another at the end of the wave. It goes back to its same starting spot. So we have matter is moved, but not transferred. And of course, energy is transferred by the wave. All mechanical waves require what is known as a medium, something for the wave to move through. If we're going to move matter around to send the wave somewhere, then we need some sort of matter or material through which the wave has to move, obviously. So it requires what is called a medium. And again, that just means something to move through. The lack of a medium is known as a vacuum, not like a vacuum cleaner, but just the lack of any material. Sometimes we talk about air friction or air resistance being negligible, or there is no air resistance in a vacuum. Okay, a vacuum just means the absence of any material whatsoever. Vacuum isn't allowed. So a mechanical wave, by definition, cannot go through a vacuum because the way a mechanical wave works is the matter is actually what transmits the wave, the flow of energy from one point to another. If there's no matter, there cannot be any mechanical wave. So some examples of mechanical waves include water waves that you're used to at the beach at an ocean, seismic waves, the waves that flow throughout the earth while some sort of seismic disturbance like an earthquake is going on. And the ones that we will focus the most on are sound waves. Okay, so that's a brief overview of mechanical waves. Now, electromagnetic waves, again, are waves in which only energy is transferred. But there does not have to be any movement of matter. Okay, no matter is necessary. Does that sound right? No matter. I'm going to put a little caret and put no motion of. Okay, so there doesn't matter. An electromagnetic wave can travel even if there is no medium, okay? No medium required. Electromagnetic waves can propagate, that means move through space, even if there is no matter for it to move. It can move matter, it can move particles, in bigger bits of matter, but it's not required. They can travel through a vacuum. Okay? So that's really interesting, and it differentiates it from a mechanical wave, in that these can travel through a vacuum, and that's very good for us. What an electromagnetic wave really is it is a combination of oscillating electric and magnetic fields. Okay, we're not going to look at electromagnetic waves too heavily, but I think you should know what they are. And the examples are the types of waves that were listed in your Regents reference tables last year on the electromagnetic spectrum chart. So the examples, the most familiar one to us is obviously visible light, but we also have radio waves, we have microwaves, not the appliance, the type of radiation, we have infrared radiation, we have ultraviolet, X-rays, and gamma rays. And again, we're not going to be looking too much at those. Electromagnetic radiation is a little bit more in line with what you might learn in AP2, I believe, and this is AP1. But before we move on, I do just want to make the point that it's always been very interesting to me once I realized this, that visible light is composed of these electromagnetic waves, this electromagnetic radiation, because what that really means, an electromagnetic wave is just an electric field. It's a disturbance in the electric and magnetic fields that cause them to oscillate, to change with some pattern. And so the visible light that we see, the colors that I see all around me, the colors that you're seeing while watching this video, what a color really boils down to is it's a representation of how frequently the light coming from that particle is oscillating. Okay, how frequently the electric and magnetic fields coming from that particle through space to your eye are oscillating. So that always just kind of blows my mind, that when you're looking at a color, what your eyes are really receiving, the information that they're receiving, is the frequency of oscillation of these electric and magnetic fields. That's what color really is. And different colors correspond to different levels of that frequency. And that's something that without science you would have no way of ever understanding that that's what you're looking at. And to me it's very, very cool that our brains can interpret that and give it something that we're just so used to for most of us in everyday life, such as color. I always thought that was really, really neat. But again, electromagnetic waves, we're not going to focus too much on those. We're going to focus more on mechanical waves, waves that move matter around but don't necessarily transfer it from place to place. We're also going to break down waves in terms of their shape. We're going to break them down into transverse waves and longitudinal waves. I don't need to write waves, I guess. Transverse and longitudinal. Now, a transverse wave is usually what you think of when you think of a wave. A nice transverse wave looks something like this. It's not a very nice looking wave. Okay? It's the wave that kind of looks, it's got, you guys will remember from last year, there's crests, the top parts, and the troughs down here. There's a midpoint line. There's a lot of other features that we could define, but we'll wait a second on those. Let's say that this wave is moving this way, so direction of wave travel. Okay? If you were to look at just one little point on that wave, let's say look at this point, and you say, okay, well, the wave's traveling to the right. Which way does this point move? And I can demonstrate this. It's not going to be a great demonstration, but I can demonstrate this with a slinky. Let's stretch this out a little bit more. If I start shaking one end of the slinky, okay, as in to make like a transverse wave like this, of course this isn't long enough. If I go like this, the individual coils don't necessarily move to the right or to the left. I'm shaking this wave so that hopefully the wave travels to the left, but the coils themselves don't really travel right or left, or they don't have to. They'll always go back to their initial position, okay? The coil itself moves more up and down than anything else in a transverse wave. So if you imagine this wave moving to the right and you've got this little particle right here, this little particle does not move left and right with the wave. It moves strictly up and down. So little piece of the wave here known as the wave element, it does move, but it's not transferred from one spot to the next. It's not moving to the right with the wave. It simply moves up and down. So what we say is that the displacement of the wave element is perpendicular to the direction of wave travel. Okay? And so this element will not move right or left with the wave. The wave can go like this. As the wave goes to the right, what this little piece is going to do, well, as the wave moves to the right, it's next going to kind of fall into this trough. So the piece will move down, the element will move down here. Then this peak will come by, it will move up to the peak. It just kind of follows the shape while staying in the same, I guess you would call this the same X position. The main type of transverse waves that we talk about a lot are light waves. And also, as you can see, sometimes you can have waves on a slinky that work kind of as transverse waves. If you shake the slinky perpendicular to its length, that will produce a transverse wave. Waves on a string, those would also be transverse waves. The light waves are transverse, and also I guess I'll put waves on string as well. Okay, so that's transverse waves. Now we're going to look at longitudinal waves. And the example here is going to be given again by the slinky. It's going to take me a minute to draw this. So we've got okay. So there's our slinky. And you can see that there's different regions to this slinky. There are some regions where the coils are very stretched out, and there's some regions where the coils are compressed. So we have, for instance, a region of compression right here, and here, and here. And to the sides of those, we have regions of elongation. Now, how to get a longitudinal wave with a slinky is a little bit different from getting a transverse wave. For a slinky, to get a longitudinal wave, instead of shaking it like this, you kind of push the slinky towards, or in the direction that the slinky's coils are stretched. So what I'm doing right now, doing this, by moving the slinky in and out, you can see that the coils are moving left and right in the direction kind of parallel to the direction of the wave. I'm sending the wave from my right hand towards my left hand, and you can see that the coils are moving back and forth, left and right with that. For a transverse wave, again, would be if I shook my hand like this, okay? That's a little bit different. So you can see that for a longitudinal wave, we have the opposite of what happens for a transverse wave. For a longitudinal wave, we have each part of the slinky kind of moving back and forth like this. So now, the displacement, I cannot write today, displacement of the wave element is parallel to the direction of wave travel. In other words, in order to make this wave travel, it depends on the matter oscillating left and right. It depends on the matter kind of bumping into each other and pushing the wave down. So again, I guess it doesn't really matter which way the wave's traveling. We'll say that this is the direction of wave travel. and the displacement of any little part of the wave is parallel to that direction of wave travel. The longitudinal waves we'll be looking the most at are sound waves. And because they are longitudinal, because they need to, the way a sound wave propagates is it, each bit of the sound wave, the air particles that are moving, knock into the next air particles, and that's how the wave gets transmitted. What that means is since the sound wave needs to displace matter to propagate, therefore it needs a medium. So a sound wave is a longitudinal wave, it's also a mechanical wave. Okay, so sound waves are mechanical waves and they're longitudinal waves. They need a medium. That's why we say that you can't hear anything in space. There is no medium for the sound wave to travel, so any sounds in space just don't travel. Okay, they don't move from one spot to the next. There is no sound in space. Let's see here. I think I'm going to call a pause on this one right now, and we'll come back with another video on the features of waves now that we've defined the types and the shapes of waves.